Add a new task in browser A and confirm that it appears in the table on that page. Open the other browser and repeat. Both pages should show the original and newly added tasks. Now add a task to either browser. Our changes should be reflected in both pages simultaneously. Hello everyone, this is Jay from BTYT Tech Library. Today we are going to create a WebSocket application in Kotlin with Ktor based on our RESTful API backend service from the previous session. So if you code along, by the end of the session, you will know how to create services that use JSON serialization, send and receive content through a WebSocket connection, broadcast content to multiple clients simultaneously. Let's code along. First, let's jump into the code and talk about the WebSocket. Access to the Ktor project generator. In the project artifact field, enter com.btyt.ktor-websockets-task-app as the name of our project artifact. In the plugins section, search for and add the following plugins: routing, content negotiation, Kotlin X.serialization, WebSocket, static content. After that, click the download button to download the project and open it. Navigate to source main Kotlin com BTYT and create a new sub-package called model. Inside the model package, let's import task.kt file from our previous session. Thanks to the serializable annotation from the Kotlin.serialization library, task instances can be converted to and from JSON, allowing their contents to be transferred over the network. Now let's work on the socket.kt file. Since we included the WebSocket plugin, a socket.kt file has been generated within source main Kotlin com BTYT plugins. Open the sockets.kt file and replace the existing application.configureSockets function with the following implementation. One thing we can briefly check together is that in Ktor version 3, the WebSockets plugin configuration has been updated to utilize Kotlin's duration class for both ping period and timeout properties, switching from Java's java.time.duration. This change enhanced the overall Kotlin integration, providing a more idiomatic and native experience. About the configuration properties, in the WebSocket protocol, data is transmitted using a sequence of frames. We can use the max frame size property to set a maximum frame that could be received or sent. A WebSocket ping is a control frame sent by a WebSocket client or server to verify the liveness of the remote endpoint. We can use the ping period property to specify the duration between pings. WebSocket masking is a security mechanism introduced in the WebSocket protocol to prevent cache poisoning attacks on intermediaries, such as proxies, that do not understand the WebSocket protocol. We can use the masking property to specify whether masking is enabled. In this code, the following steps occur. The WebSockets plugin is installed and configured with standard settings. The content converter property is set, enabling the plugin to serialize objects sent and received through the Kotlin.serialization library. Routing is configured with a single endpoint, where the relative URL is /tasks. Upon receiving a request, a list of tasks is serialized down the WebSocket connections. Once all items are sent, the server closes the connection. For demonstration purposes, a 1-second delay is introduced between sending tasks. This allows us to observe the tasks appearing incrementally in our client. Because we included the static content plugin, an index.html file has been generated within source main resources static. Open the index.html file and replace the existing content with the following. There are two WebSocket URI schemes, WS and WSS. The port component is optional. The default for WS is port 80, while the default for WSS is port 443. And the URI is called secure if the scheme component matches WSS case insensitively. The WebSocket object provides the API for creating and managing a WebSocket connection to a server, as well as for sending and receiving data on the connection. Following this, we establish event handlers for the onOpen, onClose, and onMessage events. When the onMessage event is triggered, we extend our data by appending a new row to a table through the use of the document object method. Run the app and access to localhost port 8080/static/index.html. Upon clicking the form, the application should load tasks from the server and display them in the table at a rate of 1 per second, incrementally populating the data as new items arrive. Additionally, we can inspect logged messages by accessing the JavaScript console within our browser's developer tools. With this implementation, we can confirm that the service operates correctly. The establishment of a WebSocket connection, sending items to the client, and subsequently closing the connection demonstrate a seamless workflow. Beneath the surface lies complex networking logic, but with Ktor, these intricacies are handled for us by default. What is WebSocket? Just like HTTP, WebSocket is a communication protocol that facilitates interaction between clients, typically web browsers, and servers. Unlike traditional request-response models used by HTTP, WebSocket was designed to support real-time bidirectional communication between the server and client. This allows servers to proactively send updates, such as breaking news, as soon as they become available, eliminating the need for separate requests from the client. Moreover, WebSocket is a full duplex protocol, enabling simultaneous data flow in both directions over the same connection. In essence, this means that data can be exchanged between the server and client at the same time, making it suitable for applications requiring high levels of communication between equal parties, such as real-time chat, collaborative editing, shared trading, bidding in online auctions, and other interactive scenarios. While comparing HTTP and WebSocket, it's worth noting that they aren't mutually exclusive protocols. In fact, most applications will use HTTP as their primary protocol and switch to WebSocket for real-time communication. One interesting aspect of WebSocket is how they work internally. When a WebSocket connection is established, the client sends an HTTP request to server to inquire about support for WebSocket, which triggers an upgrade of the HTTP connection to a full-fledged WebSocket connection, known as the opening handshake. Although this process is usually handled automatically by WebSocket APIs, understanding the underlying mechanics can provide insight into how these protocols interact. Once a connection is established, both parties can exchange data in real time with minimum latency until either party chooses to close the connection. While HTTP inherently adheres to the request-response model, there's an alternative approach to achieving real-time updates. Instead of the server responding with a complete response, it sends partial HTTP responses and maintains the underlying connection open. This technique, known as HTTP streaming, offers a viable solution for real-time updates. However, it falls short of being a comprehensive real-time solution. The primary limitation of HTTP streaming compared to other options like WebSocket is that HTTP is inherently a half-duplex protocol. As a result, data can only flow in one direction over the connection at any given time, much like a walkie-talkie allows a bidirectional communication, but not simultaneous transmission. How about the WebRTC? WebRTC shares similarities with WebSocket, but its main distinction lies in its ability to establish peer-to-peer connections without the need for a server intermediary. First, we jump into the implementation of WebSocket and saw how it worked on the browser. Then, we dug deeper conceptually into what WebSocket is and what the differences are with other protocols. Now, let's improve our design. Bring the task repository.kt file from our previous session into the model package. Go to the plugins package and open the sockets.kt file. And simplify the routing in application.configure sockets by utilizing the task repository. Let's run the app and check everything is working properly. Okay, it's time to get to the main event. Let's demonstrate the capabilities of WebSockets by creating a new endpoint that will showcase its features. When a client starts up, it receives all existing tasks. Clients can create and send tasks. When one client sends a task, other clients are notified. In the sockets.kt file, replace the current configure sockets method with the implementation following. With this code, we have done the following. Refactored the functionality to send all existing tasks into a helper method. In the routing section, we've created a thread-safe list of session objects to keep track of all clients. Added a new endpoint with a relative URL of /tasks2. When a client connects to this endpoint, the corresponding session object is added to the list. The server then enters an infinite loop in waiting to receive a new task. Upon receiving a new task, the server stores it in the repository and sends a copy to all clients, including the current one. If you're curious about suspending functions can be used inside coroutines just like regular functions. But their additional feature is that they can, in turn, use other suspending functions to suspend execution of a coroutine. To test this functionality, we'll create a new page that extends the functionality in index.html. Within source, main, resources, static, create a new HTML file called wsclient.html. Open wsclient.html and implement the following code. The newly added page features an HTML form where users can input details for creating a new task. Once the form is submitted, the application triggers the send task to server event handler, which constructs a JavaScript object containing the form data and then sends it to the server via the WebSocket object send method. Okay, let's restart the application. To test this functionality, we will open two browsers side by side and perform the following steps. In one browser, browser A, navigate to localhost port 8080/static/wsclient.html and verify that the default tasks are displayed. Add a new task in browser A and confirm that it appears in the table on that page. Open the other browser and repeat. Both pages should show the original and newly added tasks. Now add a task to either browser. Our changes should be reflected in both pages simultaneously. To enhance the efficiency and reliability of our QA process by incorporating automation, leveraging Ktor's built-in features can be highly beneficial. Specifically, using Ktor's automated testing capabilities can help ensure speed, reproducibility, and minimal human intervention. To integrate this functionality, we need to add a dependency to our build.gradle.kts file, which enables support for content negotiation in the Ktor client. In IntelliJ IDEA, locate the Gradle notifications icon, represented by a stylized elephant, on the right side of the editor. Clicking this icon will refresh the Gradle project changes. Next, navigate to source test kotlin BTYT directory and open the application test.kt file. To update the generated test class with the correct implementation, replace its contents with the following code. Configure our service to run within the test environment and enable the same functionality that we would have in production, including routing, JSON serialization, and WebSockets. Configure content negotiation and WebSocket support within the Ktor client. Without this, the client wouldn't know how to serialize, deserialize objects as JSON when using WebSocket connections. Declare the list of tasks we expect the service to send back. Use the WebSocket method of the client object to send a request to /task. Consume the incoming tasks as a flow, incrementally adding them to a list. Using the integer of list result type means we can only return all the values at once. To represent a stream of values that are being computed asynchronously, we can use an integer of float type, just like we would use an integer of sequence type for synchronously computed values. Don't worry, we will come back to asynchronous flow another time. Once all tasks have been received, compare the expected tasks to the actual tasks in the usual way. Wonderful! With the help of Ktor's WebSocket features and automated testing capabilities, we've made progress in improving our task manager service. Regarding the next session, I'm sure many of you would have liked to try out this feature. Yes, in the next session, we will cover integrating a database. We will take a closer look at how to connect our service easily to relational database system using the exposed library.